So here are some rules for assigning oxidation numbers. And it might look like there's quite a few rules here, but honestly, we've already gone through quite a few of them, and they'll seem a little bit repetitive as well. So it's not something that you really have to memorize, but it will be helpful to go over together. So we've already seen the first rule, and that's where an uncombined atom is always going to have an oxidation number of 0. So we've seen that when we've had metals all on their own in some of the reactions, and we've just assigned solid metals a 0. The thing we haven't seen so far are diatomic molecules. So our example here is this O2. So any of those Hofbrinkel molecules, they'll also get assigned a 0. We've seen the second rule as well, where simple ions and their charge is going to be the same as the oxidation number we give them. So any metals that we have, like magnesium 2+, that charge we have, 2+, is going to be its oxidation number, +2. So this, depending on who you've had teaching you science in the past, this is the reason why a lot of science teachers want to make sure you write your charges to be number and then the plus or minus sign, instead of putting the plus or minus sign first, because charges technically should be written with the number first, and oxidation numbers put the number last. The next two rules have to do with certain types of elements, the first one being hydrogen, where pretty much always hydrogen is going to be a +1, except if we're dealing with hydrides. So hydrides are when we've got a compound with a metal first and a hydrogen last. And in those instances, the hydrogen is going to be -1, which makes sense because any other time we've done a crisscross, the thing that's in the back is always going to be a negative charge. So still a 1, but it's going to be a -1 for its oxidation number. The second element we'll deal with specifically is oxygen, and it's pretty much always going to be -2, which makes sense. That's the charge it has on the periodic table. The only exception being if we ever see hydrogen peroxide, because we just had a rule for hydrogen. Hydrogen is pretty much always +1, which means when these are bonded up, oxygen can't be -2, or else we come out with some weird overall sum of oxidation numbers. It would have to be -1. And we'll see that rule in a second. Kind of repetitive, but the next rule being group 1 elements are always going to have an oxidation number of +1, which makes sense. Group 1 elements all have a charge of 1+, so it's the same thing. And group 2 elements, so the ones right next door, the next column, are always going to have an oxidation number of +2, which also makes sense because they're all charged with 2+. So that kind of repeats rule 2. The last two have to do with one another, and I've kind of already talked about it when we talked about hydrogen peroxide. So the sum of oxidation numbers in a compound have to equal 0. So that's the reason why oxygen couldn't be -2 here, because we wouldn't end up with a net 0 charge. It wouldn't be neutral. Here we have, again, hydrogen and oxygen. Water, there's no charge to water, so it's going to have to end up equaling 0, and we can see why. We've got 2 hydrogens, which would be 2 +1 oxidation numbers, plus 1 oxygen, which would be -2, and if we put that all together, we come out with 0 at the end. So it's a net neutral compound. Things that aren't net neutral, like polyatomic ions, they're going to end up becoming a sum of whatever their charge actually is. So our example, hydroxide, which is OH1-, its overall charge is going to have to be whatever that charge is. It's -1. So oxygen and hydrogen again, if we've got one of each, and we combine those two oxidation numbers, we come up with a final value of -1, which makes sense. That's the overall charge. So quite a few rules. Most of them just kind of make sense, or they seem just like obvious, and we've made a rule for it. And then if we have some elements that don't fall under any of these rules, like maybe transition metals usually, or some nonmetals like nitrogen, we have to look at using some algebra. So a few examples, maybe you want to pause it now before we go to the next slide, because it's actually our last slide, and go through the rules and assign every different element here a oxidation number. So here are the answers. Our first one, nickel chloride, is actually an ionic compound, so we don't have to look too far except for uncrisscrossing these charges. So nickel, sorry, has a +2 oxidation number because that 2 came from the nickel. And chlorine, always going to be a 1- charge, so we gave it a -1 oxidation number. We'll look at that on the periodic table. Magnesium, solid, just like what we've seen before in the reactions earlier, all on its own, so it's got a 0 for its oxidation number. That was rule number 1. Number 3, we've got another ionic compound, so we just have to uncrisscross this guy. So that 2 came from the oxygen, which was a rule, right? So oxygen's always -2. This isn't hydrogen peroxide, so it makes sense. That 4 came from the Ti, so we're giving it a +4. And we can double check too, right? So overall, this +4 times 2 would be +8. And it's balanced out by this 4 times -2, which is a -8. If I put +8 plus -8 in my calculator, I get 0. So the sum of all of these would end up being 0, so that's good. This guy looks a little bit crazy. K2Cr2O7, potassium chromate. Potassium being a group 1 element means it's always going to have a +1 oxidation number. Oxygen has its own rule. It's always going to be -2. But chromium, it's going to have like multiple different possibilities. And if you want to go to one of the periodic tables we had from the first day, the one from Mohawk College, there are some oxidation numbers on there. So it's a good way to kind of figure out possibilities for oxidation numbers. So we're going to have to do some algebra here. So I've kind of broken it down underneath. So I've got 2 +1s for potassium, so that's where my +2 came from. Let's pretend this 6 doesn't exist yet because we're trying to figure that one out. We've got 2 x's, so that's where I have the 2x for Cr, and 7 times -2 is -14. And I'm going to set it all equal to 0 because one of our rules, the second last one, is that for a compound, the net sum is supposed to be 0. So I'm going to have to rearrange this and solve for x. So depending on how you used to do that, there's multiple ways, but +2 minus 14, that'd be -12, and then you want to bring it to the other side, so you'd end up with 2x equals 12 now, and divide everything by that 2 from the 2x. So 12 divided by 2 would be 6, and that's where that 6 came from. The last one, we've got a polyatomic ion, right? That's not sulfate because it's a 3 now, that's sulfite. So instead of being equal to 0, this is going to be equal to -2. So we know oxygen is going to be a -2. Well, let's pretend that 4 is not here yet. So I'm trying to find sulfur. I give it an x. We've got 3 -2s. That's where that -6 comes from. And I set it all equal to -2 because that's our charge. I just want to get this x isolated so I can solve for it. So I want to bring the -6 to the other side. When it goes to the other side, it's going to become a +6. So -2 plus 6 would equal to +4. So that would be our charge for sulfur. So that wraps up everything we need to know for electrochemistry unit. So the next file down is going to be our assignment. So there's a few just short written questions, and then oxidation numbers appear right afterwards. And on the back of the page, there's 4 questions where we're doing total ionic and net ionic reactions, and then figuring out what's oxidized, what's reduced, who's the oxidizing agent, who's the reducing agent, as well as breaking it down into half reactions. And then we're done the course. Good job.